Okay, well, good morning, everyone. We're going to go ahead and get started. It is 1 p.m. UTC now, and there should be more people trickling in here as we go along. But let me at least start with an introduction, and then we'll turn it over to our presenters. Also give Chris a chance to say anything if she would like. So welcome to our fourth TRACE webinar. It's been interesting so far. The last three that we have done, I think they've been very informative. I think users have gotten a lot out of them. At least I hope that's the case. And I think you'll get a lot out of this one as well. This is the RELAP Mod 3.3 to TRACE conversion. I should point out that a lot of what's being discussed here mostly still applies to RELAP5 3D as well, the INL version of RELAP. There are some limitations there, which will be discussed during this webinar, but the focus of today's webinar will specifically be on the NRC version of RELAP5 Mod 3.3. And you have the prerequisites for this. If you already received the TRACE webinar materials, you're welcome to follow along during this webinar. You can also just take the materials offline and following this webinar, go through the exercises yourself at your own pace. And if you have any questions or feedback, throughout that process, be sure to let us know. But if you're able to keep up, we'll try to go slow enough to allow people to keep up with us. But if you're not able to, no worries, no stress. You can do this offline. There is, I think many of you probably are already aware, but there is a new RELAP5-to-TRACE conversion plugin, and you will need that to do this webinar. So if you don't already have that, then again, no stress. Just make sure you download it before you start the exercises. So today we are going to go through the process of converting RELAP5 models to TRACE. We've got several exercises. We have 5 planned. We may not have time to get through all of them, but we've got 5 planned that will exercise different aspects of RELAP5 to TRACE conversion. And there are, for the most part, the RELAP5 to TRACE conversion plugin in SNAP does a really good job of getting most of your model converted, but there are some things you need to be aware of, some things that don't, that just isn't possible for the converter to handle on its own. And so you need to know those things, and we will explain those things to you. Let's see. We also want to make sure that everybody has a chance to participate in this webinar. So if you have any questions, feel free to raise your hand, come off mute. This is informal. There's no formal process here. So however you would like to get your question asked, feel free to do so. This will be completely interactive. And if you'd like to just sit there and listen, that's perfectly fine as well. Either way. I will be monitoring the chat, and so you're welcome to pose any questions there. Okay, with that, I will stop for a moment and ask Chris if she would like to say a few words.
Oops. Hi, everyone. My name is Chris Murray. I am the code caretaker for the TRACE code, and I manage our contract that we use to support our codes that include RELAP, TRACE, and a little bit of Parks. Yeah, we've set up these webinars as a way to kind of, I think, try to get information into the hands of our user community at a more frequent pace, let's say, than we have in the past when we offered in-person training workshops, just because of the amount of cost it takes to put those on, and the challenges that we have in terms of resources, and being a government agency who doesn't what government agency doesn't have funding challenges. And so when Teams came about, and people's familiarity with it, I saw the opportunity for us to transition a lot of our training material to a more, I guess, frequent series of short webinars that tries to put this type of information in your hands that we think would be useful to users. Where we can pick off smaller, interesting topics, or shorter, smaller in complexity topics that we can we can bite off and present in a few hour time frame. But do it in a way where you're able to follow along. We lose the ability to have somebody looking over your shoulder helping solve problems, but you know, we I guess I don't necessarily feel like that's a huge barrier. So we're putting these on. We initially started to think about doing these bi-monthly. I'm transitioning my thinking to maybe do them quarterly, partly because of funding challenges and partly because of just our ability to develop training material and then put it on and schedule it within the rest of our milestones and things we have to do here. We don't yet have anything, a specific topic planned for the next one, which I would target maybe October, November timeframe, I think. And so if anybody has any ideas, feel free to send them to us. And with that, I think I've covered what I wanted to cover. Like I say, hopefully you get a lot of this. Give us feedback, because the only way we understand and know how to improve is with feedback. It's easy for us to sit here and without feedback, it's hard to know whether we really are doing a good job or meeting people's objectives. So that's all I have. Thanks.
Great. Thank you, Chris. Appreciate that. With that, I will turn it over to Mark Bolander. He will begin the training. We also have Isaac Hornbeck on the line as well, who will be helping to assist with the exercises. And Mark, take it away.
Okay, we'll take her away. As mentioned, this webinar is to talk about the RELAP5 Mod 3.3 to trace conversion. As Doug mentioned earlier, it's similar to convert a RELAP5 3D model over, but we're concentrated on Mod 3.3. RELAP was developed for a best estimate transit simulation of a light water reactor coolant systems, and models the reactor coolant system coupled with the core for a loss of coolant accidents. RELAP5 has been used worldwide throughout the nuclear industry for a long time. TRACE also is a best estimate reactor systems code developed by the US NRC, and it was in an effort to combine Track P, Track B, RELAP, and Ramona all together. TRACE has superior capabilities and accuracy for most applications compared to RELAP5. TRACE is gaining more use throughout the nuclear industry worldwide, in part due to a better RELAP5 to trace conversion capability. So our objectives today is to look at the conversion process from RELAP5 Mod 3.3 model to current to trace. And this is supported in SNAP using the R5 to trace conversion plug-in. And this plug-in is designed to convert RELAP5 models, complete with control systems, kinetics, heat structures into functionally equivalent trace models. After the conversion process, there is a report generated that details the conversion results, which can be very useful in resolving issues if there's any issues in your model. Again, the purpose of the webinar is to provide a discussion of the process of converting the RELAP model to trace using the conversion tool. And then we're going to be having some conversion exercises. We'll start out with a real simple model, and we'll end up with a a more complicated model. These models that we'll be using today in these exercises are used in the RELAP5 Mod 3 developmental assessment. So if you've got that manual, you can go and look and see what it's done there. We'll first overview the RELAP5-to-TRACE Conversion Plug-in, and interspersed in that we'll have about 3 conversion exercises. We'll look at a 9-vol and a fill drain and a manometer problem. And then we'll review the RELAP5-to-TRACE conversion steps provided in NUREG IA 0408, which is the Joseph Stephan Institute document that was put together it's a 9-step process, and we'll go over that and look at that process. And then we'll go over to some more complex models for the last 2 exercises, where not all the inputs are converted over, and you'll just get a flavor of what's needed to look further in the conversion process. I want to point out that in these exercises, not all of the issues of converting are covered here, such as radiation heat transfer, pipe and pump types, and so forth like that. We haven't covered all. We'll point out some of the issues that we ran across are closure issues, model closure issues. We haven't covered all of that, but we'll cover some of that a little bit there. But some of that's left up to you to go through and look at and familiarize yourself with that. This overview is just a note. This overview is from the excuse me, from the RELAP5-to-TRACE plugin user's manual, and you can find that by going to the SNAP model editor and in the top toolbar, and you go to help and help contents, and then the RELAP5 plugin user's manual. So you can look at that at a later time or just follow along here. Anyway, the RELAP5-to-TRACE conversion plugin is designed to convert RELAP5 models complete with control systems, kinetics, and heat structures into functionally equivalent trace models. After the conversion process is complete, again, as we stated earlier, a report is generated that details the conversion results. The report can be exported to an HTML file so you can review it and do whatever you need to do with it. This plugin that we'll be using was developed for the NRC in 2008 under contract with ATP. The conversion plugin is available on the tools menu, as shown here in the figure. When a RELAP5 model is put into the model editor, you can select tools and convert to trace. And what that does is it opens up a primary conversion dialog, which controls the conversion process. The category selection panel displays the list of categories of components in the selected RELAP5 model that can be converted to trace, as shown in this figure here. When a category is selected, each of these categories here is when it's selected, it opens a component selection dialog, which allows selecting individual components from a category of conversion. By default, all of the components in a RELAP5 model are selected. So you have all of them available to you. There may be occasion when you might want to remove an individual component from the conversion process, such as maybe components that comprise a vessel. RELAP5 uses 1D models, 1D components to model a core, for example, and you may want to eliminate those particular components and just use the TRACE 3D vessel model to convert it over to, or there may be some control system components that you may want to convert over manually to TRACE. Anyway, that option is available to you. Certain component converters allow the user to specify values during the conversion process. For example, user-defined material tables in RELAP5 define volume heat capacity as either a constant or a function of temperature. However, TRACE uses defined materials user-defined materials require specific heat. So to convert the two values, a density is required. In the conversion plugin, constant density is defined along with a constant emissivity, which is probably not the right one that you want to use, but both of these values can be specified manually in this converting process here. For example, in this diagram, in this figure here, material 2 is defaulted a density of 1e minus 4, I believe, and an emissivity of 1, I think. But you can go in and change that density and emissivity to the values that best fit your materials. After completing the conversion, the results are presented in a report dialog, and this report dialog can be exported and saved and used in the converting process. The report details each RELAP5 component that's been converted and lists the corresponding TRACE components. This information button off onto the right-hand side, it can be clicked on and it opens a small dialog which displays the conversion process for that particular component. This includes the numbers and types of components created and key component properties before and after the conversion process. For example, hydraulic components display the total volume and elevation change before and after the conversion, and the heat structure displays the total inside and outside surface areas for you. Let's go to a simple exercise. This is a vertical pipe with water over steam. It's called 9-vol in the RELAP5 developmental assessment manual. And what this model is just basically it's a vertically oriented pipe with 9 volumes. The upper 1/3 of the pipe is filled with water, and the bottom 2/3 of the pipe is filled with steam. And this model is used in the developmental code assessment to check the gravitational head effect and the development of countercurrent flow from an initial sharp liquid vapor interface to where the water drops down. This is primarily a qualitative test, and the liquid should fall to the bottom of the pipe. We'll see what happens here in this case. With this exercise and others that follow a root folder needs to be created that will be used for the output files that are created during the calculation process. The folder, I believe there is a process sent out to you to set up this root folder. If you've not done that, now is a good time to do that. I believe, and maybe this may not be the case. I believe Isaac will maybe go through that. If not, this has been done in other webinars, so you may already have one set up. But it will follow the dialogues in these exercises will follow, assuming that your root folder is set up for Web4 runs. That may not necessarily be the case, depending on how you've set it up. But anyway, we'll turn the time over to Isaac for this exercise. It's a fun little exercise.
Just a quick comment, the configuration tool.pdf document Mark is referring to is in the top level of the webinar materials that you should have received. And again, these materials will be made available after the webinar on nrccodes.com. So you'll have this available to you. But if you'd like to follow that document to get everything set up properly, you're welcome to do so.
Yes. All right. So let me share my screen here. So we're going to go through this 9-vol problem that Mark was talking about. So we're going to start here and we're going to import our RELAP5 input file. So if we come here, let's say import, we want to import a RELAP5 file. And we're going to come to our exercise 1 folder where you have the 9-vol input deck. You'll want to make sure that it's our RELAP5 mod 3.3 code. And we'll click open to import it. And we'll just include these 2 categories here. We'll set up our job stream in a second. I'll click OK. Now it generates this for us. We have our hydraulic components view and our control systems view here. If you want, sometimes these components come in a little small. If you click on the canvas, you can change your pixels per meter just to kind of give you a better size of things. You can adjust anything as needed here so that it's a reasonable size field for your model. At this point, if you want, you can always export your model notebook. Just to note, you can right-click on this here and export your model notebook. It just gives you a little bit more information about how the input model was brought into SNAP and just information about these components in a nice report format. So to perform this calculation of this model, we need to set up our job stream.
So Isaac, just real quick, we have a hand raised.
Yeah.
So go ahead, Karen.
Excuse me for interrupting. I have a question about the installation. I have recently updated my SNAP RELAP to version 5, and it is no longer recognized the RELAP5-to-TRACE plugin. The .jar file in the plugins directory, but the model editor doesn't see it. In the tools section, there is no option convert to trace.
Okay, so we can try to double check to make sure you have the proper access. You do need to make sure that when you go to the customer portal that you request NRC access to the Trace Parks plugins, and with that you should also receive R5 to Trace, and we can work with you offline to make sure that you've got that access. But at a minimum, make sure you go to the portal and go through if you go over to the left-hand navigation pane, there'll be a section for NRC requests, and you can specifically request Trace Parks. And then once that's approved, you should see it in your list. And
I have the SNAP installer, and it shows that I have already installed the RELAP5-to-TRACE plugin, but the model editor doesn't see it.
Okay, so we do have Bill Dunsford on the line, and he can assist you. Maybe we can take this off to the chat and see if there's anything he can do to help you. And I'll let Isaac continue on, and then if we can't resolve it during the webinar, we'll just reach out to you afterwards.
Okay, thank you.
Thank you. Go ahead, Isaac.
Yeah, thanks. All right, so to set up the job stream, we can, you could use this sample job stream and restructure some of the things in here, but just a simple way we can come in here and create a new job stream. We'll create a basic job stream and just this empty one here. We'll click finish. Now it brings up this new job stream view here. We have this RELAP5 model block here. So we can rename this if you'd like to something like for our 9-vol model in R5. Now what we want to do is you can come in here in this job stream that's now in this navigation window here. You can just drag this out and it'll give us our button that executes the model. So for this exercise, we've just named it this execute 9-vol R5. Another way, if you don't, because this name here is how your folder will be named that stores all of the plotting data and things like that. If you don't want to change that, you can come in here and if I remember correctly, it's under properties. Nope. Let's see, Bill, do you remember where that was that you had pointed out to change the name?
Drawing properties.
Drawing properties. So then in here, you can select this and choose specific text that you want on that button. Then the next piece, we want to make sure on here that we have our root folder selected for the Web4 runs folder. If you have another one set up, you could choose whichever one you want there. Then if we come in here and expand this job stream here, we want to create a new stream step. So if we right click on there, we can create a new one and we'll just create one for RELAP5. So we'll create that and it brings this up here. Again, we can just drag this block out into our canvas here. We can rename this if you'd like something like 9-vol R5. And we want to make sure that we have our RELAP5 mod 3.3 application selected. And we'll want to view this in job status, so click yes on that. And then it's often useful to demultiplex your files, so we'll click that. Then we want to connect our model block here to this relap block here. So you can use our connector tool up here at the top. And we want to connect the input from the model to the input of our RELAP5 block here. And just like that, we have it connected. Now everything here is now set up so that we can execute this model. So if we lock it, then we can click our execute button. It just takes a second to run it for the first time. Then it opens up our job status window here. It just takes a second to run through it. And there it's run through and demultiplexing our files. So then there we have it complete. So you can always come up here and plot any of your data that you want with appplot and things like that. In this exercise, we're going to use a different way of kind of viewing some of this data that'll help us compare the RELAP5 calculations to the TRACE calculations once we convert it. So we're going to create a new model. We'll just do new, and we want to do an animation model. This we can put some plots in there and even some animation masks for the hydraulic components themselves. So if you click OK to create a new animation model, we're going to first look up here at our data sources. This master source here is how we're going to connect it to our RELAP5 calculations. So down here we can come to this, our source run URL, and we're going to come into here to this web4 runs folder that we have. And we just did our execute 9vol R5. So we find that folder here, and then we can see this one was just completed today, just a few minutes ago. And we'll choose this channel that's not the demultiplexed one. It fits on or works with the animation models. So select that for our channel there. Click OK. Then to connect to that, you can use our connecting to data source button here. And that connects to that recent calculation that we ran. Now what we can do is we can insert a plot. You can come up here, insert graphs. We're just going to insert a strip plot. Just drag it out however big you want. And you can always just change our color right here, the background, so that we can see the curves that we'll put in there a little better. So we're going to change down here this independent base. Let's set this to 10, because you'll notice that our model here, it ran for about 10 seconds. And so that's just a good scale to put on our horizontal axis there. Now in here, we can select our plot data. And if we expand this option here, we can select our data source through this button here and choose our 9vol source right there. So we'll click OK. And then now we can choose a channel. Open this. And for this channel, we're going to look at void G, looking at the void volume in some of the cells in this pipe. So first, we're going to look at pipe, or in pipe 1, cell number 1. Click OK. And if you want, you can always come back to your RELAP5 model. Look at our hydraulics component view. And this is an easy way to see where. So cell number 1 is all the way at the top of our pipe, and cell number 9 is at the bottom, just to kind of remember where everything is. So then here, we chose cell number 1. This is the top cell of the pipe. So we're going to add another one. If you want, you can just create a new plot, or you can even copy this, Control-C and Control-V. Now everything else is set up how we want. We can just come in here and change. Oh, and you'll notice sometimes it becomes disconnected sometimes when you make some changes. So I'll reconnect to that. Now we can change our channel here. This one we'll choose our cell 9 of that same pipe to look at the void fraction in the bottom cell. So now once everything is set up and connected here, you can always change the names of these plots just so that we're clear. This will be the void fraction at the bottom. And this is our void fraction at the top, just so that we can easily remember what's what. So now that everything's connected, we're connected to our RELAP5 data source. We can run this animation right here and see how the void fraction changes over time. So we see that initially the top is void fraction is 0, it's full of water, and the bottom it's initially empty, just full of steam. And then the water quickly falls and the top cell is empty. So these plots make sense. So now we can move on to converting this model to trace. So we're going to come back to our RELAP5 model. And you can come up here to this tools menu and click convert to trace. And it'll pop up this little dialog. We'll just convert all of these. You can just click select all. And then we'll click OK. Just takes a second to convert it. And then we get this results dialog here, kind of explaining how everything was. And like Mark said, you can click on each of these and see any notes about how things were converted. And then this here, you can export an HTML report that summarizes all of this information with all of this data included in there. It can be useful, especially for more complex models that have some issues, that you can save some of that and see and remember those errors for later when you're resolving them.
Isaac, before
Yeah.
we move on, can you just go one more time through how you got to the trace part, how you converted over to that quickly? I just looked
Yeah.
away for a second and missed it.
You're good. So in the RELAP5 model, you can come up here to this tools menu, and then this convert to trace option is the one that'll do the R5 to trace plug. It'll use that plugin.
Great.
And
That's
then
so
on
simple.
there, huh?
That's so simple.
Yeah, it's nice and simple. And then you can just click select all and choose these, or if you want to select certain ones, you can. And then in other exercises, we'll look at some of these options here when they come up. But in this one, we'll just select all those simple ones, and then you click OK to convert.
Okay, thank you.
Yeah. So back in our trace model here, we can look at our hydraulic components view. We can see this is our 9-volume pipe here. And our control systems view as well. All of these signals got converted. So you'll notice in this job stream view, there's nothing in here. If you want, you can make this a little bigger so that we have some room. The nice part about this conversion is your job stream did get converted, it just doesn't show it in here. So if we expand all of these pieces here, there's 3 of these that we can pull out here to get. This is our trace model, and then we want our trace job right here, and then our single step. These 3 levels here, if we click all of them, then we can drag all 3 out at once. You can drag them all out individually as well if you want. And you'll notice that everything was connected still, just how we had done it in RELAP5. We can also rename these things like we had done before, just for our naming consistency. So here we can call this 9-vol or our execute 9-vol R5. And for our model, we can call it 9-vol. This one's not R5, this one's trace. I'll just make that distinction so that it's in a different folder. And this one we can call our 9-vol model trace. And this one we'll select our 9-vol trace. And then here on this block, we can then need to select a few other things. We'll want to select our trace application executable here. We're using version 5 patch 9. And then as well, view and job status. And then our demultiplex plot files. We can select that one too. So now that we have all of that set up here, we can lock our trace model and execute it. And I'll click OK to run it. I'll bring it up in our job status window. Wait just a second here. So see, it ran for the same 10 seconds and it completed it. And again, you can plot your files with apply here. But since we created our animation model, what we can do is come back to that, come to our animation model. And what we want to do is add a new data source because this one's connected to RELAP5. So we want a second one. We'll just do a new, we can call it master as well. And then we'll change our source run URL. So I'll expand that. We just did it in our web 04 runs. And it was our execute 9-vol trace. And you'll see this is the one that we just ran about a minute ago. And we'll select the one that's not the demultiplexed data files. So select that channel there and click OK. So now we see we have our 9-vol trace and our 9-vol RELAP5. And again, it's disconnected when we added that new data source. So we'll connect it with that tool there. And then we can add our curves to each of these that corresponds to that matching cell in the pipe. So select our top cell here, and then we'll add a new data set here. We'll come into here, and now we'll choose a new data source on that one and select our trace data source. And then in our data channel, this one, make sure I get the right one, will be this ALPN. So pipe 1, cell 1 is our top. So select that there. If you want, you can always change the color so it's easy to see the difference on this plot here. So you can just do maybe a red, it's easy to compare. So we have that set up, we'll click OK, and we see that one's added there. We'll do the same thing on the second plot. We'll add a new data channel here, choose our data source to be trace. And now this one was our pipe 1, cell 9. So do the same channel, ALPN, pipe 1, cell 9. So if we add that one in here, again, we can change our color to red just so it's comparable to the top. And we'll click OK to add that. So now with that, we can run this simulation and see how the RELAP5 and TRACE codes compare to each other in this calculation. You'll notice that they have very similar trends, but they are obviously not quite the same. That in TRACE, the water falls a lot faster, and then you see this kind of bump here. We'll be able to look at that in a second with some other piece. And then the void fraction at the bottom, they follow very closely that it both fills up at the bottom at about the same rate here. And so these plots are really useful, and they're good things to use when you convert your models. There's another piece that we can do with this that's fun to do as well, but it's often very useful with more complex models trying to find different errors that you might have. So to do this, we're first going to need a new color map so that we can have the right one for this. And here we're plotting our void fraction. Here we just have a fluid condition and temperature, and that doesn't match what we want here. So if we just create a new one, we can just call it void fraction. And then in this color map type, we can just select our void fraction for that type. Now with that, we can let's go to our RELAP5 model again. You select this hydraulic component here, and then copy it. So Control-C, and we come back to our animation model here, and you can paste it right in here. And so we have this block here, and just so we can easily differentiate them, let's add a piece of text right here. that says that this is our RELAP5 hydraulic component. And then we'll come to our trace model and do the same thing. Come to our hydraulic component, select our pipe here, copy it, and then we'll paste it back in our animation model. Then again, we can add a text right here up at the top. This is our trace component here. And you'll notice this block looks slightly wider than this in trace, and it just has to do with how cells are rendered differently in the trace and RELAP5 plugins for SNAP. So if we select our RELAP5 block here, we'll notice it has this data source, and it's selected our R5 data source, which is right. But we'll want to change our color map to our void fraction one that we just created. So we'll select that. And then in trace, notice it selected the R5 data source as well. So we want to change that. We expand that and select our trace data source. And then again, change our color map to the void fraction color map. So now we have all of that set up. We can rewind the animation with this right here. We'll just go all the way back to the beginning. Now you'll notice this shows blue is full of liquid, and then white is all gas, or the void fraction. And if we want, we can play it with this here and watch how it falls. And you'll notice as well that the trace one goes a lot faster. Sometimes it happens so fast it's hard to see. Up here with this clock here, if you click on that, we can change the playback speed here with this replay proportional to real time. So if we want, we could just change this to 0.5 or 0.25, somewhere around there. I'll just do 0.5. You click OK, we can rewind it and play it again. You'll notice it does it a little slower, and you can see how things are falling there. And just another thing to note, let me rewind it real fast. In the trace one, we saw a little extra curve in this void fraction of the top cell. And you'll notice as we run this cell right here stays darker. And so you can kind of see that the air is trying to get up as the water's falling. Just another cool thing that you can see when you create these animation masks with the hydraulic components. And that summarizes all of this here. And you can see how it all worked out. And I'll let Mark continue with the presentation. We'll look at some more exercises after that.
Okay. Is there any questions with respect to this particular exercise? This is a real simple one, and we chose that just because of the simplicity behind it. And but these others are a little bit more. They'll progressively get more complicated. Let's see. So before we move on, is there any questions or comments on this exercise? If not, we'll move on then. The conversion. We'll look at some of the conversion details here in the plugin that's in SNAP. The hydraulic components, all hydraulic components that are defined in a RELAP5 model can be converted to a corresponding hydraulic component. Trace provides supports for elevation changes, applying at the edges of the hydraulic cells through nameless variable iLev = 3, which is the same thing, same process as what RELAP5 uses for their elevation change. The hydraulic state properties from RELAP are converted to the trace state values using the steam tables that are in SNAP. This may cause some problems when the desired state is outside the subcooled and superheated regions. So be wary of that. With respect to heat structure components, they're converted into corresponding trace heat structures. The primary point of interest here is that source data for RELAP5 heat structures is converted to power components. So that's on the 700 cards in the RELAP5 heat structure, which provides the power to the RELAP5 component, and that is converted to power components. The resulting power component provides power in the same way as the original heat source. Only heat structures with uniform source data will spawn a power component. So you need to be wary of that. The heat structure source multiplier value is preserved as the axial power profile for the heat structure. And if reflood is turned on, the power profile duplicates the first and last rows. So that's similar to what you see in TRACE. For the power components, the point kinetic model inside RELAP is converted into a power component inside the TRACE model. That's where the point kinetics is implemented in the TRACE model. Each heat structure in the RELAP5 model that specified the reactor kinetics for a source location is connected to the power component. Note that the resulting power component will incorporate general tables from the RELAP5 model directly into the power tables in TRACE. Feedback tables in RELAP are dependent on moderator density and as such can't be converted directly into TRACE. But TRACE uses a combination of moderator temperature and void fraction for determining the reactor feedback. So there's going to be a little manual converting there for you to do. Control components. The control systems inside RELAP are converted into the equivalent values inside TRACE. Make note that there are several RELAP5 control components that don't have any direct correlation in TRACE. For example, the null zero that's used in RELAP isn't converted directly over into TRACE. So you need to be wary of that. The RELAP5 logical trips are converted into small control networks that produce a TRACE trip with a control component as an input value. TRACE doesn't have any trips that are logical trips like they are in RELAP5. So these show how a RELAP5 logic trip is converted into the TRACE logical trip. So it uses this and/or component here, this and/or control block here to make the equivalent the equivalent control logic, logical trip. We need to note that the following RELAP5 control components can't be converted to TRACE since they have no corresponding system. That's the shaft controller and the digital controller, digital timer. So if you're using those in your model, be wary of that, and you'll have to come up with your own shaft controller and digital timer in the TRACE, in your TRACE converted model. If you're looking in the RELAP5-to-TRACE conversion manual that's currently associated with SNAP here, it's out of date and it includes the pump component controller and the steam flow controller and the feed flow controller as not having any corresponding trace component to convert to, but that's not the case. Those are all available for you. Let's go on to our next RELAP5 to trace conversion exercise. This is what's called the fill drain problem in the RELAP5 developmental assessment manual. And what this model is, it consists of a vertically oriented pipe filled with steam at atmospheric pressure. Liquid is added at the bottom of the pipe using a time-dependent volume and a time-dependent junction, and it forms a rising level. And when the pipe is about half full of liquid, the inlet flow is reversed and the pipe drains out. This is another good model, and it's used to look at tracking the mixture level, which is important in modeling gravity-driven cooling systems as well. So we'll turn it back over to Isaac, and he can take us through this exercise.
All right, thanks, Mark. So to do this one, we'll follow the same general steps that we had done on that previous one for the 9-vol. So we're going to import a new RELAP5 model. Come here to File, Import RELAP5. Then we will come out to our exercise 2 folder, to our fill drain, and select the fill drain input file. Again, make sure you have the right code selected and click open. And then we'll just keep selecting these same two, the hydraulic and control systems categories to import. Click OK and import it here. You'll see this time we have a few more components in here, and you can always rearrange some of them as you need to. You can orient them as needed, just so that you can have them arranged in whatever way that you want them to be arranged. As well, you can change your pixels per meter to change the scale of things, and so that you can see anything better if you need. And we can just change the size of that real fast too. So we have this input file here uploaded into SNAP. Now we can set up our job stream so that we can run this calculation. So we'll do that with the same way. We'll come in here and add a new job stream, just a basic job stream, the empty one, and click Finish. Then we can name this block here for our fill drain model. Give it a name like fill drain model R5. Then we want to pull out our job stream from the navigation window here. We'll drag out job stream, and we can rename it like execute fill drain R5. And then again, you want to make sure your fruit folder, your runs folder is selected to the appropriate folder there. Then we'll add a new stream step for RELAP5. And then we can make sure that we have our RELAP5 mod 3.3 application, view and job status, and demultiplex the files. Then we can call this one our fill drain R5. So it'll be our execute fill drain R5. And then, oops, that one's not supposed to be execute. So now we have that stream step here. We can drag this one out. And then again, we'll connect with our connector tool, the input here to input on this job there. So now we have our job stream set up. We can lock this and execute this model. It'll take just a second because my computer's running a little slow, but all right, so I did that, and you'll notice it ran for 100 seconds on this model. So then I finished that. And again, for this exercise on your own, you can go and create the animation model. For now, I'm just going to open one that I have saved for this. It'll just follow the same exact process. And I just call this fill drain animation. So I'll just open it here. For a second, we're just going to look at these three plots on this side here, and we'll just look at the blue with the circle. That's the one that's our RELAP5. And like before, this often becomes disconnected, so you have to connect back to your data sources. So I'll reconnect that. And once it connects, we can look at these three plots here. Okay, then we'll just zoom in to focus on these plots here. So if we run it, let's see, it might be running a little slow. Yep, it's on our replay to halftime. So we'll restart that, get it to run a little bit faster. But you'll notice that this is our injection flow fluid velocity, so how much fluid is coming in at the bottom of our pipes here. And it starts out at 1/2, and then at 50 seconds, it drops down to -1/2 as it's pulling fluid out the bottom of the pipe. And then you'll notice as the fluid starts to come up in the bottom of the pipe that the pressure is increasing there. And then this mixture level comparison, it also increases and then reduces as it turns around at 50 seconds there. This one's just running a little bit slow, but when you guys do this, you'll probably see it run faster than that. So we'll just let that go there. So back in our RELAP5 model, we're going to convert this to trace. So we'll come up here again to our tools menu, click convert to trace, and then we'll just select all these components. And you'll notice there's a few more control systems blocks in this model than there were in the last one. And that's something that we'll actually have to look at in a second. So click OK to convert it. And you'll notice now it says, hey, if it failed to convert some of these blocks here. And it just says, hey, there was no corresponding trace signal variable for that. You can even sort this here and see these are all the ones that failed. So we'll just keep an eye out for that in a second. And as always, you can export this report just to kind of save those errors there. So click OK, and you'll notice if we go to our hydraulic components view, we have just one component on each end of the pipe. So in trace, or in RELAP5, we have these junctions here, this time-dependent junction and this single junction, and then these two time-dependent volumes. But in trace, these two got combined into one component, and these two got combined into one component. So then we get this break here and this fill right here. So now we want to resolve those issues we saw in that conversion process. So like we saw in that little menu, it just says that, hey, there are some of these signal variables. So we'll come in here. Some of these signal variables don't have an equivalent in trace. And I just have them noted in the exercise as well. So one of them is this signal variable number 7. And you'll notice it just has this variable name saying, hey, this is what it was in RELAP5. For this exercise, we don't need those signal variables for this calculation. But in your own models, you'll have to keep an eye out for what those are and try and recreate them, either using some control system or other things like that to recreate that signal, that value that you might need in your models. But in this case, we don't need them, and so we can just remove them for now. Yeah, Mark, did you have something?
Yeah, I just real quick wanted to point out that in this conversion process, because there's no equivalent, well, let me back up. Just to note that in some of these conversion processes, there is no such thing as a void J, but it tried to convert it to a general signal variable. And we talked about general signal variables in the last webinar that we had. And so just be wary that general signals are created here. For example, if you go to the level and click on the, say, general signal variable 50, or there you go, and look at the conversion process there. That's what it's doing there. So it knows that vol_lev is a valid trace component signal variable, so it's going to convert it there. That's all I wanted to point out.
Yeah, you'll notice that several of these out here have these generic signal variable types. So for this one, we'll just remove these few components. And then in yours, again, you can just try and recreate them in using other signals or things like that.
Mark, Isaac, we have a question in the chat from Aaron Wasaki. How would time-dependent junctions be handled by the converter?
Oh, yeah, I actually see there is one in this model. Is it just like grouped into the fill component?
Yes.
Yeah. What it does is when you have a time-dependent volume and time-dependent junction together there, that gets converted into the trace fill component. And on the other end, you have a single junction and a time-dependent volume, and that combination gets converted into the trace break component. So it gets both. It gets information from both of those components to fill in the needed information for the fill and the break trace components. Did that sound right? Does that help?
Yeah, that's very helpful. And I think you can sometimes have a time-dependent junction within a, like, not connected to a filler or a break. How would that be handled?
That converts
just
into a
interior
pump component in trace. Trace has a 0-celled pump component that is the corresponding to the time-dependent junction, and that's what it gets converted to if it can't be merged into a fill.
Okay, yeah, I didn't know that. Yeah, thanks. No, that's what I was wondering.
Yeah. All right. So there were two other little errors that came up in the conversion, and so you can see them with this model check here. So if we click on that, we'll see this one identifies those ones that say, hey, that it didn't have a conversion in trace, and so it gives those errors. But there's these two here, this fluid mass and then the fluid mass error. It says that there's no signal selected. But in this case, when you have no signal selected, it just takes the fluid mass error and the total fluid mass of the entire system. And you'll see that it does function as needed. We'll look at the animation model that I have, and it'll plot both of these values there. So if you want, you can always delete those 6 other components, like number 7 here and 57 were some of those that say that they weren't converted. You can always delete those if you want. So we'll come to our trace job stream now and make sure that we have it all set up here. Give ourselves a little bit more space to work with. And then we'll come in here to our job streams and open this up. And we want our model, our job, and our single step. We can select those 3, drag them out. And as usual, we can rename these as needed. We can call this one execute fill drain trace. And then always make sure you have the right root folder selected. And our model here we can call fill drain model trace. And then our job here, we can just call fill drain trace. And then on this job here, we want to again make sure that we have the right trace executable selected. We want to view it in job status, and we want to demultiplex our files. Let me just close this job stream here real fast. So now that we have our trace job stream set up, we can lock this model and execute the calculation. And it'll say there's warnings in it, and those are those ones that we saw in the model check, but we can run it anyways. We'll pull up our job status window in a second and then calculate this. Oh, so you'll notice that it gives us this error here. So I guess we do need to actually delete those few 6 signal variables for it to actually complete the calculation, because it'll try and calculate it and it won't be able to use that name right there for it. So if we just go back real fast to our trace control system, the ones we needed to delete were number 7. So we just unlock this, delete number 7, number 57, had number 9. See if we can find them all. Number 8, number 56, and last one was 72. See if I can find them all. Right there, 72. So then just to make sure we can do our model check, and yet we just have those last 2 there. These ones don't cause an error in the calculation, so we'll keep those 2 there. Then we'll lock this and execute our job stream. You'll see it's going through. We're halfway done. And then it finished about 100 seconds and demultiplexing our files. So now once this is done, we can go back to our animation model. And when you guys do it, you'll then add your new data channels to the animation model so that you can compare your RELAP5 and TRACE calculations. So here we'll go back to our animation model. Let's zoom out so we can view all of this together. And since we reran that trace one, it'll have us reconnect to it. It says it wasn't able to get. Let's make sure this is in here right. Our source run URL, execute fill drain. Let's see if it'll actually connect for us here. It says connected to trace. Let's see. Okay, it's connected now. So now with that, we have our trace data channels here selected for this liquid velocity through that cell 1 of the pipe. And we're looking also at the pressure in that bottom cell of the pipe, and then the mixture level comparison. So if we run this animation, we'll see this one's following it the same, this one's following it the same. But then you notice here in this mixture level comparison, this control block 1 is the sum of all of those. If we just step back into Trace here real fast, our control systems view, that's this control block 1 right here. So it's summing all of these generic signal variables for that volume level, that mixture level comparison we're looking at. But you'll notice it's not, this control block is summing to 0 the whole time. While everything else matches, these jumps are just because I moved off of the model while I was animating it. But you'll notice that this one is 0, so we need to figure out what that is and why it's doing that. So if we come back to trace, so this sum is summing to 0, so we could look at these signal variables right here, and it's signal variables 46 through 55. So if we open up our job stream tab again, we can just plot this directly from here, make it a little simpler. So plot with our demultiplex data here. I'll open app plot for us. Then it was our signal variables, and we said it was signal variables 46 through 55. So we can just select them all at once and click plot. And you'll notice they're all zeros. And so that explains why it's summing to 0. So these signal variables weren't quite set up quite how we wanted them to be. So if we look at this again, they do have this volume level here, but in trace, there's actually another way that we can do this. If you wanted to, you could just change the type on each of these 10 signals to, I believe it's 20, this collapsed water level, and then you have to change some other things. But what we can actually do, let's create a new signal variable and add it here. And we are going to do that same type 20, but if we look at some of the options on it, so we'll select our signal here, and it was hydraulic component our pipe 333. So select that one, click OK. But then now it gives us the cell option for the first location and the second location. So we can either do 1 and 1, just recreate all 10 of these, or you can just do 1 through 10 all at the same time. And then click OK to set that. And then now that's what this signal is measuring. It's measuring all of these 10 signals together. So just to make sure, this is 72. And if we look in here, this one says signal variable 155, so we'll change that in a second. But we'll rerun our trace calculation after we close applet. And yeah, we don't need to save those changes. So now we'll lock our trace model and run it again. It'll run for the 100-second problem time. And there, I finished that. It'll demultiplex those files. Now, if we come back to our animation model, we'll have to reconnect to our data source. And then once we're connected to that, we can just then change. Let me just change this. So this mixture level comparison will look at that signal variable and change it to signal variable 72 is what we had seen in our trace model. So select 72 for that and click OK. Now we can animate this. And you'll notice our control block we didn't change, so that one stays at 0. But then our green X here for signal variable 72, it's following it just like it had it in RELAP5. And so that just demonstrates a way that you can reconstruct some of those things in trace using some different options than the converter used for RELAP5. And again, you can import your hydraulic components here and see the pressures in the pipe as it's increasing and decreasing over time with the water flowing in. And you'll notice here we have our total mass plot and our mass error plot. That our total mass, the trace and relap calculations are essentially the same on total mass. Even though the model check was saying, hey, you don't have a signal selected for that, it did calculate it as expected. And same with our mass error. And since they're different codes calculating, obviously the mass error is going to be slightly different in each one. And so that demonstrates this conversion process and kind of being able to resolve a few little issues that you might see in some of your conversions. And I'll hand it back to you, Mark, unless anyone has any questions.
Hi, Isaac. I've got one quick question and then a little bit of a longer one. The first one is, can you make a legend for the color maps? Because if you come back to a animation, after, maybe a few months or something, you might not remember what you made unless you went into it. I guess you could.
You can drag the color map into the view.
So you can just drag our pressure color map. Let's see, we have our pressure color map selected on there. So just drag this one out here. Let's find a good spot for it.
Oh, okay.
All right.
Cool. And then the other question I had, is there any alternative way we would have been alerted to the signal variable not calculating as we wanted it to if we didn't already have an animation included for that variable? Or would it just be, good practice to look for pretty much everything that you might suspect to be off and put it into a plot?
I mean, it could be good to just try and go through and plot different things, especially those ones that you really need in your models. I don't think that there is anything that really would pop out as saying, hey, you need to, like this isn't quite working, other than us seeing that it's summed to 0. But yeah, it's kind of just go through and look at different things about your model, look at different plots of different values and things like that from your model to see if everything was converted how you wanted it. We'll see a little later on some of the last exercise we'll do, that you can run into a lot of different errors, and you just kind of have to slowly work through your model, plotting different things and say, okay, is this where the error is? And you just kind of have to go through chaining together from component to component until you find where it's at. So
Sure. Okay.
Yeah.
Well, thank you. I mean, this
What-
is a whole
Good
lot
question.
easier than going through an output file. So
One thing that you can do initially is, and Isaac pointed this out on the conversion report. He pointed out that there was several of those that didn't get quite converted over. You can take a look at those, and then go accordingly. If you need them, if you think you need them, find an equivalent method in Trace to get them, or like that. Watch out for your generic signal variables and make sure that they're where they need to be.
Yeah. All right, then Mark, I'll hand it back to you.
Okay. Are there any more questions or comments on exercise 2 that we've just gone through? That's another simple exercise to do. It just illustrates a few of the issues that you may run into, and we'll get more complicated ones as we go along here. Let's look at some conversion special considerations. Despite the similarities between RELAP and TRACE, there are inherent differences between their input specifications that may require some modification by you, either before or after the model conversion. Most simple models, like we've seen in the last 2 exercises, are converted over automatically without any additional action required. However, as you get into your more complex models, you'll more than likely see places where that you're going to have to do some model editing, and some of these areas, primary areas of concern, include cell elevation changes, treatment of multiple inlet and outlet connections, unsupported RELAP5 signal variables like we've seen, radiation enclosure beam lengths, heat structure general tables, control system engineering units. It can give you some heartburn, and unsupported components. If we'll go over each of these briefly and look at what the concerns are that you may be watching out, that you probably need to watch out for. Multiple inlet and outlet connections. RELAP5 allows any number of hydraulic connections to any face of a volume. This includes internal edges as well. This behavior can be mimicked with crossflow connections in TRACE. When the orientation of the source and target cell is different, the elevation change across the crossflow connection may not be preserved. Multi-junction components are converted inside SNAP. For example, consider the case of a horizontal pipe connected to the inlet of a vertical pipe in RELAP5. When the connection is converted to a crossflow in TRACE, you'll notice that the horizontal pipe is assumed to connect at the cell center of the target pipe rather than at the end. This is going to result in a net elevation change of 1/2 the target cell length. So be wary of those kinds of things. Radiation enclosure beam lengths. TRACE radiation enclosures define both the view factor arrays and the beam lengths between heat structure surfaces. RELAP5 radiation only defines the view factors. So in the conversion process, TRACE, the plugin will fill in the beam lengths array with 0 to allow the model to pass TRACE input processing. TRACE accepts those 0 beam lengths array, but this input is interpreted to mean that the fluid between the surfaces do not participate in the radiation heat transfer. So therefore, as users, if you feel that that's important to you, you're going to need to make those changes manually.
Hey, Mark, just to jump in here for a second, going back to multiple junctions, Luis has a question. So in cases with multiple junctions, how can it be done if crossflows are not desired?
In the conversion process, if you've got more than one, like for instance, if you've got a branch that has multiple junctions and they're going to a pipe component and they both connect to the inlet of that pipe component, one of those is going to be connected normally in TRACE, and the other junction, branch junction, is going to be converted to a side junction with an angle of 0 or 180, depending on which way things are going. I don't know. I don't think there's any other way of getting around that without having cross connections.
So it may just be a situation where you need to remodel it manually to get the desired connection.
That's right.
Mark, this is Jay. I may not understand the issue, but on those side junctions, like when you say it has an angle of 0, then that side junction is connected to the inlet of that fluid cell. And if
That's
you
right.
say it's 180 degrees, then that side junction is connected to the outlet of the fluid cell, the TRACE fluid cell. And if you say 90 degrees, then it's connected to the center of the fluid cell. And as you orient that side junction around, TRACE is calculating what it thinks the flow path is from the cell center to that side junction. And when it's at 90 degrees, as you pointed out earlier, then you have a different flow path for that side junction than if you had it at 180 or at 0. So that has as you noted, has an impact on the elevation change.
That is correct. In fact, in some of these, in a couple of these models that we'll get to a little bit later here, we've had some issues like that we've had to resolve, where things didn't quite match up, and when we modified the angle, then it worked for us. It gave us the loop closure that we were after. Appreciate that, Jay. That's what a good thing to note is how those 0 90 and 180 connections, how they're treated in TRACE.
I think it's also important to note that TRACE does not check for elevation loop closure, and but SNAP does. And so if you just run your TRACE model and the loop is not closed, TRACE will run it, and you'll have an artificial gravity term in your model. But you can check the elevation, the loop closure in SNAP, and that's always a good thing to do after you're converting these models.
Yeah, that's correct. So if you're trying to model gravity flow situations, then you need to make sure that your converted TRACE model is doesn't have any loop closure issues in it, because that becomes important. Each structure general tables in RELAP are shared lookup tables that return the appropriate dependent value when provided with an independent value. In this way, a general table that determines, say, heat transfer coefficient based on temperature can be used by multiple heat structure surfaces, and each with a different temperature value. However, TRACE general tables require either a control block or a signal variable, which provides a constant independent variable value source. So each TRACE general table has a single value for a given time step based on the value of its independent variable source. So a general table which determines heat transfer coefficient based on temperature would provide the same value for heat transfer coefficient for every heat structure surface that uses that general table based on that independent variable source. So that's something to keep in mind. A partial solution is to extract the general table into a function type control block, which uses the appropriate surface temperatures as the independent variable value. That's something you need to be wary and consider in your conversion process. Unlike TRACE, RELAP5 control systems don't include engineering unit specifications for constants, gains, minimum and maximum values, and this can be a burr under the saddle sometimes if you're not wary of that. It can create some numerical conversion errors when converting RELAP5 control systems from a model using British units, for example. So you need to be wary of that. The converted model should be carefully reviewed to ensure that the control systems behave properly. In the last two exercises we've got, there's some examples of that where you need to be wary of those constants, gains, and min-max values that don't have engineering units in RELAP, but are required for the RELAP, in the TRACE converted model.
Hey, Mark, just real quick, Aaron has a question.
Hey, yeah, so just to make sure I understand, so SNAP can convert units like within SNAP itself, but you're saying if a control variable, like a control variable value will not be converted because it doesn't know the units, is that right?
That is correct. And
Okay.
and that brings up the issue of if I've got a RELAP5 model that's in English units, do I convert those? Do I convert that model to SI units before I do my RELAP to TRACE conversion problem? And does that help anything? And the answer there is not necessarily, because of the constants and gains aren't necessarily they're unitless in RELAP5. Does that make sense to you?
Yeah, thank you. Mhm.
Okay. All right. So that last little bit there on this slide here, I think we've already covered that. If you're having issues, one thing that you can do to troubleshoot is to convert your RELAP5 model to SI units. And that in some cases that helps, some cases that you're just going to have to be wary of what's going on there. The RELAP5 turbine component and feed water heater components aren't currently supported by the converter plug-in, so you want to be wary of that. And in fact, in the first part of this discussion that we've had, you can, when you go to convert your RELAP5 model, in that dialog box, you can select or deselect the components that you want to that you want to have or that you don't want converted over. And maybe this might be one case where you might want to go in, and if your RELAP5 model has a turbine component or a feed water heater component, you may not want to convert that over. But you have to do that manually if that's you need it in your model. One other thing is that RELAP5 mod 3.3 patch 6 has added 2 new valve types: swing check valves and the tilt check valve. These components aren't converted to trace, so watch out for those types of components. The following converters have been partially implemented, but require further development. So these are some issues that you need to watch out for. For example, the pipe converter, it needs to be modified to support the pipe type flags that are available in TRACE. These will enable the conversion of CANDO channels and accumulator components. The converter needs to be adjusted to support these final decisions regarding bent pipes, as we discussed above. The pump converter, further investigation is required to ensure that the pump converter correctly converts all types of RELAP5 pumps to TRACE. There's some differences in the TRACE pump types and the RELAP5 pump types that aren't necessarily going to be compatible. And with the valve converter, it's further analysis required to ensure that all valid valve types are correctly supported by the conversion utility. So these are just areas that you need to be wary of and double check in your converted relap or in your converted TRACE model. The kinetics converter, in order to convert the reactivity feedback from RELAP5 to TRACE, there needs to be at least 2 rows in the density and Doppler reactivity feedback tables in your RELAP5 model. We ran across one case, and in fact, that's one of the problems that will in our exercises, where there was just one entry and it didn't convert over properly. So the problem was that the 2 rows are needed in these 2 tables to identify the powered heat structure in the TRACE power component. The RELAP5 to TRACE converter converts reactivity from dollars in RELAP5 to delta K over K in TRACE using a total delay neutron fraction beta of 0.0065. So you need to be wary of that. The fluid and Doppler temperature coefficients in the 701 to 799 cards and the 801 and 899 tables in RELAP are not automatically converted to TRACE, but you can convert these manually using heat structure or volume averaging of the coefficients. TRACE uses a single averaged heat structure and hydraulic volume quantities for the independent variables used in calculating the reactivity feedback. This is determined by averaging across the powered heat structures identified on the power component and the hydraulic volumes attached to those heat structures. So be wary of these kinetics converters and what you need to do there to make them work properly in the converted trace model. Let's go on to exercise 3, which is the manometer. And what this this is another developmental assessment problem in RELAP5, and it's used to check the non-condensable state calculation and the code momentum formulation for periodic flow and the level tracking model. What this model is it consists of 20 volumes. The first 10 volumes are oriented vertically downward, as shown in this diagram, and the other 10 volumes are oriented vertically upward. Volumes 1 through 5 are filled with dry nitrogen, and volumes 20 through 19 or 20 through 16 are also filled with dry nitrogen, and everywhere else is filled with water. In this problem, to initiate the oscillation, an initial velocity of -1 meters per second is placed at all of these junctions, and note that to perpetuate the oscillation, wall friction is turned off in the model. Okay, we'll turn the time over now to Isaac to lead us in this exercise, and we'll just go from there.
All right. Thanks, Mark. So we'll follow the same process that we've done in the last two. We're going to import our RELAP5 input model. So we'll import, this is in our exercise 3 manometer. So we'll import that, make sure you have the right code selected. And then just our hydraulic components and control systems will import. We have this here. We'll increase the size a little bit so we can see it a little better. And this pipe here, it's kind of hard to see, but it is both pipes looped down and up. There's just no separation between them, just a 180-degree turn at the bottom, and both sides are overlaid on top of each other right there. So you can always rearrange your components however you need. So now we want to set up our RELAP5 job stream so we can run this model. So we'll come over here to job streams, and we can add a new job stream, just the basic stream and an empty one. We'll get this in here. We can rename this one to our manometer model R5. Then we can drag out our job stream from right here. And then again, you want to make sure you have the right root folder selected. Then we can call this one our execute manometer R5. And then if we open this up, we can create a new stream step. We'll create a new one for RELAP5. Then we want to make sure that we have our mod 3.3 selected. We'll view in job status and demultiplex. Then we can drag this piece out here, and we can rename it manometer R5. And then we want to connect our inputs to input here. Use our connector tool. input to input there. So now we have this set up here. We can lock our model and execute it. It'll just take a second to run. And you'll notice it runs for about 100 seconds for that problem time there. So just like on the last one, I'll just open up a previously saved animation model, but you can follow the same steps that we've done before to add the same plots and the hydraulic component masks and things like that into your model. So we're here in our exercise 3 manometer. We just open up this one here. So we'll need to connect our data source so that we can get our new RELAP5 data. All right, so it's this red one right here with the circle, and then we're also we can also look at the void fractions, and these ones right here. This is our cell 11, so it's one of the cells at the very bottom of the pipe. And then these three on the void fraction are cells 5, 6, and 7, so they're right in the middle, right around where the water is oscillating. So we'll see these kind of oscillate back and forth. So when you run it at the turning points on the plot, you'll notice that it'll run a lot slower just because of how tight it is there. But we can see with our red here, it's oscillating back and forth with that fluid velocity oscillating around 0. So it started at that -1 and increased to 1 and just oscillating back and forth like that. And you can see that the void fraction, the cell 5, is initially all void. It's all nitrogen there, no water, but it's oscillating back and forth right there. So we'll just pause that. And if we go back to our RELAP5 model, now we can convert it to trace. So we'll come in here, use our plugin here, tools, convert to trace, and we'll just select all of our components. As well, you'll notice there's a lot of different control systems that were included here. So click OK to import this. And this one, you'll notice everything converted successfully, or the converter says that it didn't have any challenges converting any of these pieces here, which that's good, but we'll still notice that there's something that's not quite working right when we get to that point. So we can go to our hydraulics components view, and you'll notice again, these components are different than they are in RELAP5, that the junctions and the volumes were converted to these breaks here. So they're joined together into this one component in trace. So to run this one, we'll need to reconstruct our trace job stream. Can give a little bit of space there to add it here. We'll come in here and look at our model. So we need the model, the base job stream step, and single step. We'll drag those 3 out. Now we have them here with the connection still there. So now on this one, we can rename these as needed. You can call this an execute manometer on the button. Make sure you have the right root folder selected there. And then on the job here, we can call it manometer trace. And then you want to make sure, again, select the right application. We want to view it in job status, and we will demultiplex our files. And then on this model block, we can just call it manometer model trace. So with everything set up here, we can lock it and execute the trace calculation. And on this one, there's no errors on the initial run there, but we'll see how it runs and see what happens next. So this one will also run for the 100 seconds. So it ran 100 seconds. We'll just keep that window there, but just minimize. So if we go to our animation model, we would then add our new trace channel here. So our fluid velocity of pipe 777, that cell 11 at the bottom. So we'll reconnect to get that trace data. Then we will run it. And you'll see the trace data is blue here, and it just dropped to 0, shot from -1 to 0, and just kind of sitting there right at 0. And so obviously something's not quite working right how we expect it to. So we'll pause this, and let's look at this data channel specifically and see what is there. So we'll come back to our job stream, job status here, and we'll plot our trace data. So that was on our pipe 777. We can see it's this channel VLN pipe 777 cell 11. So pipe 7, we'll go to our VLN channel and our cell 11 for that liquid velocity at the bottom. So if we plot that, we can just zoom out for a second. We see that it comes from -1 to 0. If we just zoom in just to see what's happening right here real fast, you will notice there is actually some mild oscillations there, but something happened where it just drops almost immediately to 0 on velocity. So to do this, we'll look at, let's just close this here. Let's go back to our RELAP5 model and look at something. So in our hydraulics components view, this pipe right here, if we look at the initial conditions, so right here we selected our pipe initial conditions. If we expand that, we can see here's our pipe, and we have this quality column here going from cell 1 at the top, going down to cell 11 at the bottom, and then again our cell 20 at the top. And we have a non-zero value on our cells 6 through 15. So this is where the water is, and so the quality is saying, hey, this is all gas up here, and this is all water right here. So if we close that, and let's look at our trace model. All components will do the same thing. We'll look at our pipe, and here we will look again at our initial conditions. So right here, we'll expand our initial conditions. And the columns in this table here are different than they are in RELAP5. But we'll notice this gas volume fraction column says that everything is 1. So it's thinking everything is full of gas rather than any water or anything. So we will need to change that for the cells 6 through 15, the ones that are initially water. So if we come here, we can just put a 0 on that. If you want, you can always copy and just select all the way through 15 and paste that there. So now we have all of those as zeros for our bottom half of this YouTube. Then we can save this and rerun our trace calculation. Yeah, Mark, did you have something?
Yeah, just a note, and I think everybody that's run RELAP5 is aware of this, that in RELAP5, when you want a dry non-condensable, RELAP5 has a flag that if you put in 0 for the quality, it recognizes that as a dry non-condensable. And so in the RELAP5 model that we just looked at, that's what the 0 is saying, not that it's a 0 non-condensable, it's just dry non-condensable. And so in order to specify liquid, you have to be just slightly above 0 to get all liquid in there, which we saw with the 1E-9 input there. That is some of the issues of the conversion. So be wary of that. Go ahead.
Yeah, thanks for that, Mark. All right, so we set that now on our trace component here. So we'll come to our job stream and we'll execute this again. Pull up our job status. We'll run through again for about 100 seconds. Then we can compare them in our animation model. So we'll come back to our animation model and reconnect to our data sources. So it's connected and we'll run it. And we'll see that the trace is following very, very closely the same path as for that fluid velocity that we had in RELAP5. And so it's calculating it correctly right there. And as always, you can add an animation mask for your hydraulic components and see how it is here. And you'll notice our junctions at the top tell us which direction the fluid is flowing in and out of each side as it's switching back and forth. An important piece to note on this model is that one of the uses of this model is to demonstrate things with level tracking and trying to make sure that the fluid, our water in the bottom, doesn't diffuse or disperse kind of into our nitrogen gas that's at the top half of the pipes in here. And if you don't have the most recent R5-to-TRACE plugin, you will have an extra step where you'll have to turn level tracking on in your trace model because that doesn't get converted in the older RELAP5-to-TRACE plugins. But this is just an important one to demonstrate how the level tracking is working. Because if it wasn't, these void fractions in trace, it would start to reduce. It wouldn't ever get all the way back up to 1 here. The liquid would kind of diffuse into the vapor up at the top. And so that demonstrates that, and trying to see another area to watch out for when you're converting your models from RELAP5 to TRACE. So I'll hand it back to you, Mark.
Okay.
If anyone has any questions?
Yeah, are there any questions or comments on that? I think these 3 exercises are rather simple, but show some places where you may want to watch out for in your models that you're working with and converting them over to TRACE.
We do have one question here from Aaron.
Okay.
Hey, yeah, since some quality was mentioned earlier, so I was wondering how so when you specify a boundary condition in TRACE, it's, void fraction and the phase temperatures. RELAP lets you specify other ways such as static quality. Does it attempt to convert those like with steam tables, or how does that work? And also, does it always assume water? What if you have a different fluid?
I believe it'll try to convert it using the steam tables. Is that correct, Bill?
Yeah, it tries to do it. It does the best it can. Obviously, the steam table, the TRACE initial conditions require certain properties, and it uses the steam tables to convert those over using a fairly old copy of the RELAP or implementation of the RELAP steam tables. As if you're using a different fluid, that's not going to work so good.
Okay. I figured, but yeah, thanks. That clears it up.
But it's just for the initial conditions. So at the worst case scenario, you just have to enter your own initial conditions and get a steady state.
Well, it could be for the boundary conditions also, right? For the fill.
Oh yeah, same.
Mm-hmm. All right, thanks.
Okay. And any other questions or comments? Okay, moving on. We'll now take a little bit of time and look at the work that was done at the Joseph Stefan Institute and in the conversion process that they've developed and put together for everybody. That's NUREG IA 0408. But there's 11 steps that they put together to help you in your conversion process, and we'll just go through those 11 steps here. The first one is you first need to adapt your legacy input model to RELAP mod 3.3 input models. There are some changes between legacy RELAP5 input models that are put together earlier than mod 3.3 that need to be adapted to run on 3.3. So be wary of that. The other thing is that the SNAP conversion routine doesn't recognize RELAP5 code versions earlier than mod 3.3. The second one is you import your adapted RELAP5 ASCII model into SNAP. A couple of things here is that the model imported into the SNAP environment and a graphical display is shown of the hydro and control systems. Any comments that you might have in your RELAP5 input model need to be that you'd like to preserve will need to have the comment structure that SNAP will recognize. Otherwise, that's a star D : and then your comment. So you can go into your ASCII RELAP5 model and add that in front of your comments if you want to preserve those. Sometimes you'll see that your RELAP5 model will have comments at the end of a line. And we run into a case here where it was the asterisk followed by the comment, but it was the asterisk and then the comment without any break between the comment and the asterisk. That didn't fly. SNAP didn't recognize that. So you'll need to go through and adjust any of your comments that you have out at the end of a line to have a space between the asterisk and your comment. And then once you import your RELAP5 model, you're going to want to rearrange your components because it doesn't know what your model looks like, so they'll be in a disarray. So you want to take the time to go and rearrange your components so that it looks familiar to you and to others that are going to be using your model. Note that once you get your RELAP5 model rearranged, your hydro components rearranged in a view that looks familiar to you, then that will transfer during the conversion process. Then it's suggested that you export the RELAP5 model notebook. Isaac pointed out how to do that in a first exercise, and it's going to be useful since your information about the RELAP5 model is presented it's presented in a well-organized manner, and it helps you when you're looking for errors or issues with your converted trace model. You can do a comparison between what your model notebook, your exported model notebook says, and that. If you some of your models may already have a pretty good detailed input of your, or detailed inputs of your model, so that would be helpful as well. And then it's always a good idea to perform your RELAP5 calculation before you convert. That way you've got a basis for a comparison with RELAP5 to your trace calculation to make sure that everything is running the way you expect it to be. The other thing that you can do to help in this is create an animation model for your RELAP5 calculation. This is optional, but as we'll see here in the next little bit here, that having an animation model helps you find errors that might occur in your converted RELAP5 calculation. And creating if you've not created an animation model before, as Isaac has shown us here, it's fairly simple process. All you got to do is just go in and copy and paste your hydrodynamic view of the model into the animation mask. And then you can add to that other animation features such as strip plots and a bunch of stuff that you can add to. Excuse me. And then you can go in and create, you can convert your RELAP5 model to trace. And this step uses the conversion plugin, as we've pointed out earlier here. And besides converting the RELAP5 input model to trace, input the model editor views are also converted, including the hydraulic component view. Now, it may not look exactly like your RELAP5 because it's going to be adding some single junctions in the conversion process into your RELAP5, into your trace model, and so it can kind of look a little messed up, but it won't take long to rearrange your components and make it look reasonable. And then the next thing, that this is the most important step, as Isaac has pointed out in some of these exercises, that we need to check for and resolve trace model errors. Checking a trace model for errors is done using the SNAP model editor check model command, as Isaac pointed out. Typically, the converted trace model isn't error-free, so be wary of that. All errors identified by SNAP are manually corrected. Note that the check model command does not identify all inconsistencies in the converted model input. So be wary of that. So here's where, once you get your model converted over to trace, it's a good idea to export the model notebook. And that way you can use that. It's useful in helping to compare with your RELAP5 model model notebook and see if you can find. It helps you find the inconsistency between the two models, and you look for that in your geometry, control systems, and so forth, things like that. And then once you've got you feel satisfied that you've got your errors fixed, then go ahead and run your trace calculation. And more often than not, you're going to have some more errors that trace is going to point out. So you may need to. You're going to have to iterate on this step until all of your errors are eliminated. And then again, it's recommended. Again, it's optional but recommended to develop a trace animation model. And it's simple by just going in and copying the trace hydraulic view and pasting it into animation model. Note that the first trace calculation probably is not going to satisfy you. So therefore some manual work is probably going to be needed to further modify your model or add additional components. Note that the above steps are described for the whole model, not a restart model. Typically, RELAP5 ASCII restart input files don't include the whole model, and therefore you can import that into SNAP and convert it into a trace restart model. Therefore, your trace transient or your restart model has to be built manually. So keep that in mind as you're doing this conversion process. These last two exercises are integral effects problems used in the developmental assessment. And these are more complex and introduce conversion issues that you may encounter when you're converting your own RELAP5 models to trace input. The first one, the exercise 4, is the semiscale natural circulation. It's the full power and full liquid primary side, and the exercise 5 is the TIP 1200. I think many of you have looked at the TIP 1200. What it is, it's a PWR 4-loop power plant. 3 loops are modeled as 1 loop, and the other loop is modeled as a single loop, and it contains a 4-inch cold leg brake. Depending on the time that we've got available to us, we'll do exercise 5 first. If we can get through that, then we may do exercise 4. If not, why then you can use exercise 4. Do exercise 4 on your own. So we'll turn the time back to Isaac to look at to start this exercise, this TIP 12. TIP 1200 has point kinetics in it, so that's why we chose to do this one first, because it has the kinetics in it. So Isaac, we'll turn it over to you. And
right. Thanks, Mark. Yeah, hopefully we should be able to squeeze this in enough time before the end of the webinar. All right, so like Mark said, this is the TIP 1200 one. This is significantly more complex than the last 3 models that we just did, but we'll go through and learn some useful things. So we'll import our RELAP5 input model, and it'll be in our exercise 5 TIP 1200 input deck there. So we'll open that. And again, just do our hydraulic components and control systems. This one's quite a bit bigger, so it'll take a second longer to import it all. So, and here we have all these components, and you'll notice everything is just kind of spread out. You can manually rearrange it, but just for just to see everything better, we've saved a view template, and it should be included in your materials as well. So if you come to Tools, you right-click on the background, come to Tools, and then say Import View Template. Then you can use this R5 Hydro model view template file. So open that, and it rearranges it somewhat well. Sometimes I've had it come in better than others, but
you may want to go to your tip 1200 exercise 5 to get that.
Oh, did I grab the wrong?
Yeah, it was the semi-scale.
Import view template. Oh, yep, I was in semi-scale. All right, exercise 5. That'll definitely. I was like, I wonder why it's coming in wrong. R5 Hydro. There we go. Thanks, Mark. All right, so there we can kind of see the whole system here with our 2 loops on the sides, and then our main here in the center here with our core and everything. So we will look at next to build our RELAP5 job stream. So we'll come over here, and you also notice real fast that our control systems view, there's a lot of different components in here. There's a significant amount. So we'll create our job stream. We'll create a new job stream, just a basic job stream, and an empty one. We'll finish that. So now we have our RELAP5 model. We can call it our TIP 1200 model R5. And we'll add our job stream execute button here. We can rename it execute TIP 1200 R5. As always, make sure you have your right root folder or your runs folder selected there. Then we will add our stream step, add a new stream step for RELAP5. We'll select our RELAP5 model. We'll view it in job status. And then we'll also want to demultiplex our plot files. And we'll call this job step our TIP 1200 R5. Then we can drag this one out and connect our input from the model to our input on the job. Now we have our job stream set up. We can lock this model and execute it. This one doesn't take too long to run. All right, so it ran for the 1200 seconds there. Now it's demultiplexed our files there. We'll just minimize this for now. And we'll just open our previously saved animation model, just since these larger models take a little bit more work to build the whole animation model, because we've included, for example, in here we can see all of our different our hydraulic components that we've added here and have everything set up with the right channels. So here we're just going to be looking at our primary side system pressure and the secondary side system pressure, as well as the brake mass flow rate and this core outlet void fraction. So we'll connect to our data source since we just ran our RELAP5 model. And once it connects, we can run it and we'll see our blue here is our RELAP5 data in each of these. We can just ignore the red for now. That's what our trace model will look like once we finish everything and get it all worked out. But we can see that the system pressure decreases on the primary side initially and kind of just gradually decreases after that. And the secondary, it increases initially and then gradually drops down. And then this flow rate through this break in the primary side, the flow rate is decreasing and drops closer to zero, but we see that it doesn't drop completely to zero. And then this void fraction on the core outlet, we can see that initially it's zero, it's all liquid, but then it does end up getting up to 100% void fraction, but it's all steam coming out of that core outlet there. So there's a couple things to note about that. So now that we have this running in RELAP5, we will convert our model to trace. But there is one piece that Mark had pointed out that's really important in this model, and it's the reactor kinetics. So we'll see here under reactor kinetics, there's some data in here that we have set. Then our Mark had mentioned this density reactivity and this Doppler reactivity, where they need 2 rows in these tables to be able to get converted when using that conversion tool to trace. So we'll notice in here that we just have 1 row in each of these. And since the reactivity on these is 0, what we'll do is we'll add a new row, and you can just add some value close by. And then keep the same reactivity there. And we'll save that and then do the same for our Doppler reactivity. If you forget to add these rows here, the converter will convert it. You'll see a few errors with some heat structures, and then it'll be really hard to recreate the same reactor kinetics in the trace model itself. So it's just a lot easier if you remember, could add these extra rows to your tables here before you convert it. So now that we have that in there, we can come up here to tools and convert our RELAP5 model to trace. And you'll notice here we have a lot more components in here. So we'll just select all of them. And you'll note it says this is unconvertible, this general signal null 0, which is normal. We don't need that one in trace, and so that's fine. Another piece to note is we have 5 materials here. So if we come to this options tab down at the bottom, we see that we have this materials section here. So there's 5 user-defined materials, but you'll notice all of these have the same default density and emissivity in here, but that's generally not the value of density that you want. And it needs this so that it can convert all of the right material properties to the values that we need in trace. So in the exercise document, we have a little table that kind of gives a best guess of the densities for these materials based on how they're used and what they're probably for. So we'll go through for material 1. We have a density of about 405. For material 2, very light material. Make sure I get the right value there. For material 3, it was 661. Material 4, 524. Then our last material 5, about 499. So we have all of these densities in here. And if you need on your models, you can always add the right emissivity that you need there. For this one, we don't necessarily need that, so we'll just leave that there for now. So we have all the materials density set. Now we can click OK to convert to trace. All right, so it's converting everything. We'll get our results here. And you'll notice this one, it only has this one null 0 that wasn't converted, and that's fine. Everything else, it says that it didn't find any issues in the conversion process. And when you do this one, trying to find different errors, it may be really useful to export the report just so that you can compare things more easily with what it used to be in RELAP5. So we'll close that. We'll come to our hydraulic components view, and we've also provided a view template for this if you want to use it. But everything in here is generally in a nice place. You could rearrange it as you want for your models, but we'll just leave it like this for now. So we need to rebuild our trace job stream so that we can execute this one here. So we'll come to job stream, give ourselves a little bit more space here. And then we'll bring out the components from here, take our model, our job, and our single step. Okay, so now we can rename these as needed. We can call our model our TIP 1200 model, single step, that's our execute. And then our base job we'll just call TIP 1200 trace. And then again for this one, select our trace executable. We'll want to view it in job status, and we will demultiplex our files. So we have that all set up. And we'll lock that and execute this one. And you'll notice it says there's some some warnings. So what we'll first do, we'll let this run. We'll look at some of these warnings in a second too. This won't end up running for very long. It'll kind of freeze up. And then we'll have to just force stop, but we want some of the messages that it gives in here. So when we run it, it says, hey, there's something wrong with this fill component 188, and then it mentions this junction 890 that's with component 188. So let's look at our model, component 188, and that's up here. So if we zoom in, this is our component 188 right here. You notice it looks like it's connected. It has the blue dot right there that's filled, but we don't see an actual connection. And it did say the junction 890. So if we look up here, we want our connections menu right here. We expand that one, and our hydraulic connections. We'll expand that one. We'll look for hydraulic 890. So it's down here near the bottom, and it says it's connecting pipe 180 to fill 188. So it says it's connecting these two components together, but we can see that it's not. And the reason why is because in RELAP5, this one was connected to this outlet here, and this should actually in trace be connected to the side because we can only have one connected to this outlet right there. So what we'll do is we'll come over here, right click on our connection 890 and say disconnect. Now you see it disconnected from that piece there. And now we'll manually connect with our connector tool 188 to the side of pipe 180. And then what we want to do is this angle right here, like Mark had talked about earlier, we can set this angle to 180, saying that we're actually connected to this pipe outlet right here. And since in here we have these two loops, this one on the left and this one on the right, if we look over here, we'll notice we have the same kind of thing here. This fill 288 with 280. If we look right here, it's this connection right here. Pipe 280 to fill 288 is connected. So we'll remove this connection and just do the same thing. We'll disconnect that, manually connect the fill to the pipe, and then change our angle here to 180 to say that we're actually connected to that outlet right there. So we have those straightened out. So the next piece, let's look at our model check. So if we use this check model button up here, we can see what's going on, why it gave us those errors when we tried to execute it. You'll notice it has these 4 loop check errors, talking about the elevation going around a few of these loops. And if you want, you can go through and try and see if you can find a way to resolve these. For now, we'll just leave them. They don't immensely affect the calculation of this one, so we'll just leave that as an exercise for those who want to. So we'll notice we have this abrupt area change test, and it's saying this pipe 310 edge 3. So if you click on that line, it'll actually bring you right to it. And if we expand our friction attribute right here, we can see, so it referenced this edge 3 right here. And so if we change this K factor right here to just something really small, like a 1 E minus 4, just to kind of have it a somewhat gradual change from this value to here to 0. So click close on that, and we can refresh the results right here, and we'll notice that that resolved that abrupt area change test. So that's good there. So we'll leave these loop check errors there for now, and everything else looks good. There's some warnings here you can look at as well if you want. So we'll close that. We can lock our model and execute it again. Come to our job stream and execute. And those warnings were just from the loop closure check. So we'll run this. It'll take just a second. You'll notice so it started times 0, and now it's printing out a lot of other messages here. So it's saying it's flipped some trips. And now you'll see the total time it's gone through is just like 16.25 seconds, but then it's printing out all these messages saying, hey, pipe component 280 has something going on with it. It says gas temperature failure, and well, if you let it run, you might even notice some things about 270 or 180 or 170, things like that. So what we'll do for now, we'll just force stop this calculation. Let it finish that and stop it. So what we want to do, let's go back to our animation model real quick. So we have this one here. If we connect it, we'll be able to see some of these values that TRACE is giving us for the pressures, void fraction. So if we run it, we'll see the red just stops almost instantly, right about 6 seconds, 16 seconds there, because the TRACE calculation didn't finish. And we'll notice the pressure on this one just jumps up really fast right there. The rest of these are kind of following what we might expect. And so what we can do is if we look at our pressure animation, this is one way that these animations here with these hydraulic component masks can be really useful. So I'll rewind the animation. And if you want, you can use this skip forward button here to just step by one animation time step at a time. And you can watch how things are changing between these two codes here. So we have it started at 0. We'll step. And as we step through a few, you'll notice things aren't changing too much. But then you'll notice right here on this step, some things changed in these components there. And even some of these junctions here in RELAP5, you'll notice a little switch on them coming up there. As we step through, you'll notice these valves changed between 12 and 14 seconds. And then we notice a big pressure jump from 14 seconds to 16 seconds. That did not happen in RELAP5. So we see something on these two secondary loops is happening there. Something we saw these valves are now open. We saw that switch there too. So we'll look at some of these things around here and see what's going on in there to see if we can find out that. So we'll come back to our trace model. So we will look at some pressure, since we saw that pressure jumping up really fast. So there's a few different components you might see mentioned in this job status. We saw 280, and sometimes you might see a 270. So if we look around those components, let's come over here to pipe 270. Is right here. We have pipe 270 here and pipe 280 right here. So we see a bunch of pressure flowing in, a bunch of pressure. So there's must be something adding mass to the system there. So we'll look at our fills, because those could be something that would be adding some mass to our system. So we had just done something with our fill 288 right here. So let's pull up our job status and just plot some of these values here. So in Trace, we'll open up our plot data. Take just a second here. So that was our, if we come back here, we have a fill 288. We have this fill 282, this fill 284. Let's look at these two real fast, 282 and 284. So we'll come in here. I'm going to fill 282 and fill 284. We're going to look at the mass flow rates here, which is our FX mass. So if we plot 282, it starts up here and decreases. It doesn't at first look anything abnormal with it. So we'll look at our 284 as well. And that one's just flat down there. So let's compare this with our RELAP5 data. If we come up here to File, we can say Read RELAP5 data. And then we can go and select our TIP 1200 R5. TIP 1200 R5. And we'll import that one. Now we want to look at the same corresponding data channels, but in RELAP5, which these ones are the channels M flow J. So we scroll down, look for our M flow J, and we'll notice that in RELAP5 we had junctions next to some volumes, and the M flow J's channel here corresponds to the junctions, which don't correspond to the same exact number. So 282 in RELAP5 was the volume, the time-dependent volume, and so we'll actually look for 281. So we'll find here 281, and then for 284, the corresponding one is 283. So we'll select both of those and plot them. And now our scale for RELAP5 went to 1200 seconds. So let's just zoom in here and see what's going on. And you'll notice in RELAP5, this 281 and 282, it should be constant for a little bit and then drop. And then this 284 to 283, it should actually be 0 initially, but it's not. And so something's up with both of these fills, 282 and 284. So if we come back to our RELAP5 model, let's look at those two, 282 and 284. And see, let's look at their fill tables. If we zoom in and look here, we have this table right here. So we have pounds per second, and it's a non-zero value, and then it switches to 0, and this is on 281. So if we come to trace, so that corresponded to our 282 here. And we have a mass flow table type selected right there. So let's look at our fill table. And you'll notice that it has this. This value is different because the units right here are pounds per hour. And so the value was converted correctly, but if we look, the RELAP5 component there had a trip selected. Let's come back to that. 281 has this variable trip 501, but in trace on 282, we don't even have an option for a trip. And so it turns out that this fill type isn't the type that we want. It's actually type 8, this constant mass flow with trip. And so we'll change the type to that, to our constant mass flow with trip. And then now we'll see down here at the bottom, we have a table trip signal that we can select. And so we had seen trip 501. We'll select that one there. And then we'll also want to make sure that find the right one here, this initial coolant mass flow should be the right value corresponding to this table. So if we expand this one, here at 0, it is, it does have that same value. So that one looks good. Now on 284, this one has the same thing. So if we look at RELAP5 just to make sure, 283 uses logical trip 608, and the table starts out at 0 and then goes to a non-zero value. So if we come to trace, this one will change our fill type on fill 284 to the same type 8 with mass flow, constant flow with trip. Then we can select our table trip, which was trip 608. So select that trip there, and then we'll look as well here. These values are right. Again, this value is different because the units are per hour rather than per second, like it was in RELAP5. And initially it's 0, and we can see right here, this initial coolant mass flow is also 0, so that's good. And since we had seen kind of a mirrored issue with these ones on both secondary loops. Let's just go to the other side and compare these ones as well, 184 and 182. So we'll see again, these are this type 5, but we can just make sure in RELAP 5, we'll look at those corresponding components. Here, this 183 uses trip 608. So again, we do need that same type, that constant flow with a trip. And same with 181, this one uses 501. So we'll come back to trace. 182 should be type 8, constant mass flow with trip. And then we need to add our table trip, and this one is trip 501. And then the 184, change the type to type 8, and add our new table trip, and this one was trip 608. So we've set those there. Then there's a few other things with some of these components that we can look at. So with these, let's look, if you right click on one of these components, you can click this show ASCII, and it'll give us kind of the input file format, the ASCII format of that component right there. So we just looked at 282. Let's compare it with the same ones for the 182. So in here, we'll look at this here. Let's move this one up and look at 181 as well with it. So in comparing these, we'll see this fine difference between them that can be a little hard to catch sometimes. So we have right here this geometry, we have this dx in and volume in right here, 3001. So if we look right here, 181 is the component that's actually connecting to this pipe 174. And 182 is this volume here that's connected to that junction. So you'll notice this has a length of 1 and an area of 3000, which is where that converter got this volume 3000 and a length of 1. That's how it calculated those right there. But we'll notice that that's actually not quite right, because the area of this junction is 2.208, not 3000. So what we need to do is recalculate this volume right here with this area and that length rather than that area. And so this time it's just 2.208 times 1. So if you double click on this value right here, it'll bring us right to it in trace. So just double click that. So it's this 3000 right here. And we said we wanted it to be a 2.208. So I'll save that one, and now we'll see it's updated there. So we can look at the same things with other ones around here. So we just did 182. If we look at this one, it has the same thing. It says 3000, so it has that same conversion there, 2.208, which you can check by looking at the geometry here with that flow area of 2.208. Then we'll do the same thing on this side. This one has a flow area of 0.736. And then if we look at this one's ASCII here, it still has a length of 1 and an area of 1000. So if we look at trace on the other loop side, 282, we have right here, we have this volume of 1000. And so we see that that one is also miscalculated, and it should be, let me pull up that value again in RELAP5. our 0.736. We can just copy that and we'll see it's the same on both of those. So we can do the same on here. Set that to 0.736 and same with this one, 0.736. So we have all of those geometries and things corrected. So we can run it again. Since it takes a second, I'll just let you know that it comes up with still very similar issues, still referencing some of these same components. So we're just going to keep looking around those loops to try and find what else might be wrong. And since we had done some things with this fill 280, and we just had to correct some things with these other fills, let's look at that one and compare some things as well. Let's start out by plotting our mass flow rate through our 288 here, and then the corresponding one in RELAP5 is our 287 right there. So bring this back up, we can just clear everything. So we want our fill 288. We'll look at our mass flow rate there. And then our 287 is the corresponding one in RELAP5. We'll plot that one. See if we zoom out, because it just shifted it. It's hard to see, but right here is where the trace one is. And then that's where the RELAP5 one is. So obviously, there's some more mass flowing into the system than what we expect right there. So we'll look at that fill 188 and 288. We look, let's just come back to our model and trace. We have fill. So if we look at our fill table, we can see these values here. So it's based on a pressure that we get this flow rate. But if you look, this is saying a pressure in units of PSI of this one, even right here, of 2.9 e to the minus 3. Like, that's just an unphysical value because our atmospheric pressure is around 14 PSI. And so this is clearly, something's clearly wrong with these values here. So if we come and look, let's just check what we have in RELAP5. On here, this fill table, this is the flow rate that we saw, and that was correct. But then this search variable, it doesn't have any units, and so these weren't quite converted to the values that we want. So what we can do is these are the actual values in PSI that we need. And so in your models, you have to make sure that you know what your units were in this search column here, so that you can make sure that you convert them to the right values in trace. And you'll just have to be aware of that. So if we just copy these values here, you can just select and copy, come back to the trace. And we just, let me make sure I copied it from the right one. We did 287. So that's our 288 in trace. We'll open our fill table. And we'll just paste these values right into here. And that just makes it a nice and simple way to copy it over. So we'll click OK. We've set those values, and we'd probably expect the same thing to be on this side with 188. And so if we look at that fill table, we notice the same kind of thing. These pressures are not the right values, and you'll actually notice they're the same as they are on the other side. So we can just paste these same values in right here, and we can check that in RELAP5 just to make sure that we have the right ones. On 187, and we can see those are those same values that we had copied, so that's good. So now we have all of those straightened out. Let's go to our trace job stream. Let's lock our model and run it. And I guess we'll have to close our app plot first. It's using the trace data, so I'll try again. Take just a second to run. It's quite pull up our trace calculation yet, but it'll get there in a second.
So Isaac and Mark, we are at our 3-hour kind of limit here, and I don't know if there's anything else you want to just say in terms of concluding this model. I know you probably, the exercise itself has more things that that the users can walk through to try to diagnose a model, but I think that the takeaway here from my perspective is for large complicated models, plant models, and integral effects test models and things of that nature, you're bound to run into issues like this that Isaac has been demonstrating. And so you do have to put on your troubleshooter hat and try to understand, you know, what is happening in your model and what to look for in the model, you know, what clues you could be looking for to help diagnose what the issues are. So Isaac is giving you a really great example here of the TIP 1200 model. And there is more to diagnose in this model that you can, you know, do in your own time following this webinar. But again, you know, it's just one of those things that you're going to have issues, expect them, and then just, you know, be keen on looking in the right places to resolve the issues. Isaac, was there anything else you wanted to comment on just in general to kind of sum this up?
Not really. Some of the other issues that we're run into are just, again, with some of the other fill components. And then there was also some things with some of the pump types, just the wrong type was selected. And then even with that, there's probably going to be more things that if you wanted to, you could find some other issues between the RELAP5 and TRACE models here. Just try and look through it and find other differences that you can find. We don't go through everything, but just make some notes about some possible places to look to continue that. And the semi-scale model is very similar to this one, kind of going through similar issues, trying to resolve fills and pressures. And I think there's probably some valves in that one too, but they're very comparable. So with that, you could probably get through both of them.
Okay, great.
Just a quick comment on this. The first view of our animation model that Isaac showed us on TIP 1200 showed the final results of what we had obtained by making all these corrections, and it didn't look too bad as a first cut. So that looks pretty decent for kind of a first cut. More improvement can be made by following the 11-step process that Joseph Stefan Institute identified, and moving on from there.
Right. And as always, you know, if users are converting models to TRACE and they're running into issues and they're just not able to figure out what's going on, feel free to reach out to us, send us an email, and we'll be happy to take a look at that and try to help you diagnose what the problem might be.
Just to point out, the last few slides on our presentation is just kind of a recap of what we've already talked about. You can go through that on your own. The last slide points out some of the issues that have been resolved from putting this presentation, this workshop together. So take a few minutes and look it over if you'd like.
Okay, great. Well, thank you, Mark and Isaac, and also a special shout out to Mark. For those that don't know, he is retiring at the end of this week. And so he will not be available for these future webinars, and he's done such a great job, and I really appreciate all the work you've put into these, Mark, and all the work you've put into your career over the years. You've been a great resource for us here at ISL, and Mark is one of the preeminent experts in trace and relap analysis, and we're sad to see him go, but if his wife gets tired of having him around all the time, then maybe he'll come back and help out for future webinars. But for now, we thank you, Mark, and wish you well in your retirement. And thank you, Isaac. Great job on all of this. And we're going to go ahead and close the webinar for now. Again, all these materials, we'll put together a final package of materials that includes kind of final med files and final animation med files as well that you can then play around with in your own time. And then the recording for this webinar will also be made available on nrccodes.com. And with that, we'll say thank you very much, everyone. We appreciate you participating, and enjoy the rest of your week.